Okay, this video is going to be an introduction to drawing Lewis structures. And Lewis structures are just representations of molecules, and molecules mean that these are going to be all covalent compounds that show all the electrons, bonding and non-bonding. So the difference between what you guys did yesterday with the circling, the sharing electrons, and today is just a little bit of the format, and there's a more kind of formal process to figure these out. So let's get into that process. So there's a couple of rules. So the first thing when we write Lewis structures, we're going to find the sum of the valence electrons. So we're going to add together the number of valence electrons for the entire either polyatomic ion or molecule. Remember, ion is going to have charges, so this could be something like NO3 minus, okay? If it's an anion, you're going to add an electron for each of the negative charges. If it's a cation, you'll subtract from the overall. So let's look at our example over here, PCl3. So phosphorus has 5 valence electrons. There's 1 phosphorus. And chlorine has 7, and there's 3 of those. So it's going to be 5 plus 21 for a total of 26 electrons. So before we can be completely done with this Lewis structure, we have to make sure that all 26 of these electrons are accounted for. So when we draw this, we're going to put the central atom as the least electronegative. So this is the element that doesn't want the electrons as much as the other elements. It will never be hydrogen. So hydrogen can never be a central atom. It'll always be one of the outer. And then we're going to connect that central atom by single bonds. A single bond is just a straight line. And it represents 2 shared electrons. So before, where we would do like, chlorine sharing an electron, we will now draw it as a line between the two. So these are kind of the same representation of the same thing. So remember, we said that we're starting with 26 electrons. We need to keep track. So there's going to be 2 in this bond, 2 in this bond, and 2 in this bond for a total of 6. So we've got 20 electrons that we need to take care of. So that's what we're going to do next. So next, we're going to start on the outside because the outer electrons are going to be the most electronegative. And we're going to fill their octets. So remember, octets mean 8. So I'm putting in my 1, 2, 3, 4, 5, 6, and then the line counts for 8, or for 2, 7, 8. And so if we go to the bottom, chlorine, there's 2 in this bond, and then 4, 4, 6, 8. 2 in this bond, and then 4, 6, 8. So I've used 2, 4, 6, 8, 10, 12, 14, 16, 18 more electrons while I did that. So that means I have 2 electrons left. So I'm not quite done yet. So after you fill the outer octets, if you have electrons left, you're going to fill the octet of the central atom with those electrons. So I'm going to put those 2 on my phosphorus. And now phosphorus has 2, 4, 6, 8. So everyone is happy, and I've used all 26 of my electrons. So down here was my count. This was my bonds. These are my chlorine, and then these ones were on my phosphorus. So the goal would be to have everyone's octet filled and have all of those electrons taken care of. So let's try it. So our first step is going to be to count up the electrons. You guys, I want you to actually show your work on this so that when I'm looking over, I can see, okay, here's where they made the mistake. They counted wrong. They subtracted wrong. So you're always going to show this. So there are 4 for carbon. Each chlorine has 7. So 7 times 4 is 28 for a total of 32 electrons that I need to keep track of. So between carbon and chlorine, carbon is going to be my least electronegative. And then I'm going to attach my 4 chlorine. Okay, so 32 minus 2, 4, 6, 8, because I have 4 bonds, 24 electrons left. So now I'm just going to start putting them in my outer atoms. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20, 21, 22, 23, 24. So I have 0 left. So I want to do a quick check, make sure my octets are filled. So each of my chlorines have 1 bond, which is 2, plus 3 more sets of electrons. So 6 plus 2 is going to be 8. And then my carbon has 2, 4, 6, 8. So 4 bonds, 2 per bond, for a total of 8 electrons. So everyone in this one is happy. This is kind of the most straightforward. So on your worksheet today, this is going to be the section A, bonds. Now, there is a chance that you might run out of electrons before the central atom has an octet. So let's go through how we came to this process here. So hydrogen, so if we're looking at the compound HCN, hydrogen has 1, carbon has 4, and nitrogen has 5. So that's going to be a total of 10 electrons. Carbon is our least electronegative. It is farthest to the right. So it's going to go in the center, and I attached my hydrogen. So I've got 1, 2 bonds, so that's -4. That leaves me with 6. And then I'm going to put my lone electrons on my on my most electronegative. So hydrogen is happy with its just 1 bond. So I'm going to put those 6 on my nitrogen. 2, 4, 6, 8 with that then on my nitrogen. So nitrogen has 8. Carbon, because it has 2 bonds, only has 4. And hydrogen only has 2. Hydrogen is okay with just having 2, but carbon needs to have 8. So I can't add any more electrons. So what I'm going to do is basically drop these electrons into the bond. And so what I'm going to create is a double bond, which is 2 pairs of electrons being shared. So when I do that, my nitrogen has still 2, 4, 6, 8. My carbon has 2, 4, 6. And my hydrogen still has 2. So nitrogen's still good, hydrogen's still good, but carbon needs some more. So I'm going to drop in another pair of electrons. And when I drop them in, I'm just making nitrogen share. I'm not taking them away from nitrogen. So that is going to get me to this point here, where hydrogen has 2, carbon now has 4 bonds, so that's 8. And then nitrogen has 3 bonds plus 2 paired electrons for a total of 8. So everyone is happy with 2, 8, and 8. This is going to be section B of your worksheet, where you're going to have to work with double and triple bonds. A quadruple bond is not a thing. So if you ever get to that point, you've done something wrong. But double and triple can definitely happen. Okay, so let's try one of these. So carbon has 4. Each oxygen has 6. So there's 2 of them, that's 12, for a total of 16 electrons. Carbon is going to be my central atom, and I'm going to attach my 2 oxygen to it. Okay, so those 2 bonds are going to cost me 4 electrons for a total of 12 left. So now I'm going to split those 12 between my oxygens. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. So I've used all my electrons. This oxygen has 8. This oxygen has 8, but carbon only has 2 bonds, so that's 4. So carbon is definitely not happy with that. So I'm going to drop in from this oxygen. It doesn't matter what side I start with. And it's going to end up being like this. Okay, so this oxygen has 8. Carbon now has 3 bonds for a total of 6. And oxygen here has 8. So we're still not happy, which means we're going to drop in one more pair. We want to kind of keep this balance since it's oxygen on both sides. So I'm going to take a pair from my other oxygen now and drop it in. And what I'm going to end up with is an oxygen double bonded to a carbon, double bonded to an oxygen. And let's just double check. So this oxygen has 2 bonds, which is 4, plus 4 more electrons for 8. Carbon has 4 bonds, which is 8. And then oxygen has 2 lone pairs, or 2 pairs, and then 2 bonds for a total of 8. So everyone is happy. Now, we said we wanted to kind of keep that even, and that's a general kind of understanding, but there is a way to check if you've kind of kept it even correct way. This is something called a formal charge. So a formal charge basically is the difference between how many electrons the atom brought in and how many electrons are actually assigned to the atom. So we're going to take the number of valence electrons, and that's from the periodic table, minus the electrons it has in the Lewis structure. The formal charge can be 0, which is ideal, or it can be negative or positive. Negative meaning it has more electrons than it started with or than it brought, and positive meaning it has less electrons than it brought. The ultimate goal would be for everything to have formal charges of 0. So we're going to count the lone pairs, and those are kind of my 2 dots, and the half the electrons shared in the bonds. So we look at this one here first. There's oxygen brings 6 valence electrons, and it has 1, 2, 3, 4, and then it has 2 bonds, so that's 2 more. So it has 6 for a formal charge of 0. Carbon brought 4, and it's got 1, 2, 3, 4 bonds, so that's 4. And then oxygen brought 6, and it's got 2, 4 in the electrons, and then 2 more bonds for 6. So this one here where we kept the sides even, everything has a formal charge of 0. If we had taken or shared those electrons from the same oxygen instead of switching to the other side, we would have a different outcome. So in that scenario here, our second scenario, this oxygen came with 6, and now it's got 2, 4, 6, plus this bond for a total of 7, meaning it has a formal charge of -1. Carbon came with 4 and still has 4 bonds, so carbon is good. And oxygen came with 6, but now this oxygen has these 2 plus 3 bonds for a total of 5, and it has a +1 charge. So when you're trying to decide, did I do the structure correctly, you want to have the structure that has the lowest formal charges. So this one that I circled here, this is going to be the best structure. That would be the correct structure. Okay, so the Lewis structure, the best one has the fewest charges. If you do have to have charges, the negative charge should be on the most electronegative atom, meaning the one that wants the electrons the most or has the strongest pull. It is okay to kind of erase and redo to try and make those formal charges work out. You guys, there are 2 more videos posted here if you want to watch. Try a few on the worksheet, and if you're still having trouble, this SO2 is going to be a double bond, and the SO4 2- is an ion. The only difference is that you're adding 2 more electrons, but it is an interesting one to watch.